In this question, you can see that we have to match the column 1 and column 2. So in column 1, in option number A, it is given that there is a rod of length L and it is suspended from the ceiling by one of its ends, and Young's modulus of the rod is gamma and its density is rho. So the elongation of the rod due to its own weight is this one. So we have to find x. So we have already discussed this question in the previous videos, that when a rod is being suspended from the ceiling, then it gets elongated due to its own weight, and that elongation, let's suppose this is the rod and its mass is m. So this is equivalent to an elongation produced by a mass of m by 2 in a massless wire of same length. So this elongation delta L will be equal to stress into original length upon gamma. So delta L will be equal to stress, which is mg by 2 into original length is L and divided by gamma. Now you can see that a density of this is given. So stress, we are talking about stress, therefore there would be another term of area, A. Okay, so this is the stress. Now mass is not given, in fact its density is given. So if we talk about density, then density is equal to mass upon volume, and mass is equal to density into volume. So volume is area into length, and this is G and this is L upon 2A gamma. Cancelling this A with A. So delta L will be equal to rho A G L square. In fact, A is cancelled. So rho G L square by 2 gamma. So if we compare it with this one, rho G L square by 2 gamma, then you can see that x in this case will be equal to half. So the correct matching of option number A is option number S in column 2. Now in the next part, B part, it is given that a light wire of diameter D and its Young's modulus is gamma is stretched horizontally between two clamps, and the distance between the clamps is L. Now a weight of a mass of m is suspended at the midpoint of this wire, as a result of which the midpoint is descended down by a distance of this. We have to find x. Now in this situation, in part B, it is given that there are two clamps and a wire is fixed between these two clamps, but due to application of a mass m at the midpoint of the wire, it is descended down by a distance of x. Let's suppose it has descended by a distance of y. Okay, so this is L by 2 and this is L by 2. Area of the diameter of wire is given as D. Now you can see that D is the diameter of the wire, this one. Now you can see that in a simple way we can talk about that if this angle is theta and this angle is theta and this angle is L dash, this length is L and this length is L. This is extended length, the length which is the final length of the wire. Okay, so we can say that L cos theta is equal to L by 2, and therefore L is equal to L by 2 sec theta. So extension in each wire is L minus L by 2. So I can say that extension in each wire will be L by 2 into sec theta minus 1. And the strain produced will be x upon L by 2. The extension in the wire upon its original length. So it is equal to sec theta minus 1. Now the stress produced in the wire, sigma, is equal to strain into Young's modulus, and the stress sigma will be equal to this sec theta minus 1 into Young's modulus. Now let us suppose that a tension of T is produced in this wire, and this is equation number 1, and it is balancing out this mg. So you can see that the component of T along this side will be T sin theta and T sin theta. So the net component will be 2T sin theta, which will be balancing mg. And here you can see that T will be equal to mg upon sin theta into 2. And the stress will be equal to, stress is tension upon area. So stress will be equal to, this is T and this angle is 90 minus theta. So this is T sin theta, 2T sin theta is mg. So stress is T upon A. So T upon A sigma is equal to mg upon 2A sin theta. And this is equal to gamma into this one. So gamma into this sec theta minus 1. So you can see that it is sec theta minus 1. Now we can write down this sec theta again as mg. Now you can write it down as mg by 2a sin theta is equal to gamma into 1 minus cos theta upon cos theta. And you can see that this is mg by 2a sin theta, and this is gamma into 2. You know the formula that I'm writing it down with another ink, that cos 2 theta is equal to 1 minus 2 sin square theta. So sin square theta will be equal to 1 minus cos 2 theta by 2. So sin square theta by 2 will be equal to 1 minus cos theta by 2. So I am writing down the value of cos theta, 1 minus cos theta, which is 2 sin square theta by 2, and divided by cos theta. And now you can see that mg by 2a sin theta is equal to gamma into 2 sin square theta. So for small angles, sin theta is approximately equal to theta, and therefore it is theta by 2 whole square divided by cos theta. And mg by 2a gamma is equal to 2 into theta by 2 whole square into tan theta, and tan theta is also equal to theta for small angles. So mg by 4 a gamma is equal to theta square by 4 into theta. So cancelling this 4 with 4, so you can see that mg by a gamma is equal to theta cube, and theta is equal to mg by a gamma to the power 1 by 3. Now theta is equal to mg by area, which is pi d square by 4 gamma to the power 1 by 3. So theta is equal to 4 mg by pi d square into gamma to power 1 by 3. Now theta can be written as, for small angles, theta can be written as y upon L by 2. So this is y upon L by 2 is equal to 4 mg by pi d square gamma to the power 1 by 3 and y is equal to L by 2 into 4 mg by pi d square gamma to the power 1 by 3. Okay, so you can see that if we compare it with this expression, this one, so the power is x by 5 and here the power is 1 by 3. So x by 5 is equal to 1 by 3, so x is equal to 5 by 3. So the correct option which matches with this option number B will be Q. Okay, now in the third part you can see that there is a horizontal rod of length L and mass m and Young's modulus gamma. It has a cross-section area of A and it is rotated with n revolutions per second about the vertical axis which is passing through its middle. So we have to find out the elongation in the rod. Now we have already studied this topic and we can see that we have already studied that for a rod which is hinged and which is fixed to rotate about the axis passing through the end, the extension produced in this rod, let's suppose its density is rho and gamma is gamma. So the extension produced in this rod is 1 by 3 rho square. We have already discussed it in the previous videos. So we can use that form directly, that the total extension produced in this rod will be rho omega square L cube by 12 gamma. So we can use this directly if the rod is rotating with the central axis. So let us assume that rod is rotating about the central axis and therefore the total extension, L is the length of the rod. So the total extension produced in the rod will be this one, rho omega square L cube by 12 gamma. This is x is equal to rho omega square L cube by 12 gamma. Now omega is 2 pi f and the revolutions is given, frequency is given as n revolutions per second. So we can write down the omega as 2 pi n. So x is equal to rho into 4 pi square L cube into n square by 12 gamma, and cancelling with 12, it is rho pi square L cube n square by 3 gamma. Okay, so if we compare it with this one, okay, now the mass is given. So we have to eliminate rho. So we can see that rho is equal to density is mass upon volume, and volume is L into area. So x will be equal to L, this is m into pi square and L square, because one L will be cancelled out, and n square by 3a gamma. Now if we compare it with this expression, n square m L square by gamma a into 2x. This is equal to, this x is extension. So don't get it confused with, so I am writing it down as delta L to avoid any confusion. So this is delta L. So we are comparing it with this one, 2x n square m L square by a gamma. This is 2x n square L square by a gamma, 2x n square L square by a gamma, 2x n square L square m by gamma a, m also will come. So you can see that cancelling this n square with n square, L square with L square, and m with m, and a gamma with a gamma. So x is equal to pi square by 6. Okay, so you can see that we have to assume the pi square as 10. It is given in the question. So if we write it is 10, then 10 by 6 is 5 by 3. So again, the correct answer for this one will be option number Q. Now for option number D, it is given that there is a horizontal ring of mass m and radius r. Young's modulus of the ring is gamma, and the cross section area of the ring is a. It is rotated with an angular speed of n revolutions per second about its central axis, which is vertically passing through its center of mass. So we have to find out the increase in its radius. Now let us first of all consider a ring, that there is a ring and it is rotating with an angular speed of omega, which is equal to 2 pi n. Okay, so we have already derived the result, but I am again deriving it for this question. That let us suppose that we are talking about this part of this ring, small part, which is making an angle of d theta at the center. So on this part, you can see the tension will be acting tangentially like that, and this angle will be d theta by 2, and this will be d theta by 2. The net component of the tension in the downward direction will be 2t. This angle is, you can see that this angle is 90. This is 90 minus d theta by 2, and this is d theta by 2. This is also d theta by 2. So this is 2t sine d theta by 2. It is balancing dm r omega square. So 2t sine d theta by 2 is equal to dm. dm will be m by 2 pi into d theta into r omega square. So for small angles, this is 2t into d theta by 2, and this is m d theta r omega square by 2 pi. So cancelling this 2 with 2, d theta with d theta, t will be equal to m r omega square by 2 pi. And the stress will be equal to tension upon area. So T upon A will be m r omega square by 2 pi A. This stress will be acting on each small part of this wire, and let us suppose that this small length of the wire is r d theta, which is dx obviously, and the extension in this part is dy. So what I am saying, that I am assuming this length as dx and the extension produced in this length will be dy. So the strain produced will be equal to dy by dx, and strain will be dy by dx will be equal to this sigma upon gamma, where gamma is the Young's modulus. So dy will be equal to sigma by y into dx. Now if we integrate both the sides, like dy is equal to sigma by gamma into dx, and now if we integrate both the sides, so dy is the extension in a small part of dx, so the total extension will be delta L, and the total length of the wire is L. So delta L will be equal to sigma by gamma into L. Now we know that L is the total length, which is 2 pi r, and delta L is the change in length, which is 2 pi delta r. So 2 pi delta r will be equal to sigma by gamma into 2 pi r. Cancelling this 2 pi, so delta r will be equal to sigma by gamma into r. Now sigma, we have already calculated that it is equal to m r omega square by 2 pi a. So this is m r omega square by 2 pi a into gamma and into r. Now you can see that omega is equal to 2 pi n. Now if we substitute the value of omega as 2 pi n, this one, then delta r will be equal to m r square into 2 pi whole square into n square divided by 2 pi a gamma. Cancelling this with this and comparing it with this expression, which is x into mn square r square by a gamma. It is equal to x into mn square r square by a gamma. So a gamma and a gamma is cancelled out, n square is cancelled with n square, r square with r square, m with m. So x is equal to 2 pi. So the correct option which matches with this option D will be option number R. So now we move on the next question. In this question, you can see that there are two wires A and B of negligible weight and they have same material and therefore their gamma is same, but their radius are different. The radius of wire A is RA and radius of wire B is RB. There is a block between them which has a mass m and a force F which is equal to mg by 15 is applied on the lower wire. One of the wire will break. One of the wire breaks. It is given in the question. Now let us first of all write down the forces. So the tension in wire B will be equal to F because F is directly applied on this wire. Therefore it is mg by 15 and the tension in wire A will be equal to F plus mg. So it would be equal to 16 mg by 15. The tension in wire B. So the stress produced in A will be equal to 16 mg by 15 into pi RA square and stress produced in B will be equal to this is mg by 15 into pi RB square. So if RA is equal to RB, okay, so if RA is equal to RB, you can see then this stress sigma A will be equal to 16 mg by 15 pi r square and sigma B will be equal to mg by 15 pi r square. So you can see that sigma A is 16 times of sigma B. So A will break if RA and RB are equal. Now if RA is 4.5 of RB, RA is equal to 9 by 2 of RB. So let us first of all substitute the value of RA. So RA is 16 mg by 15 pi RA square. Now I am substituting RA as 9 by 2, so it is 81 RB square by 4. So it is 64 mg by 15 into 81 into pi RB square. And we already know that sigma B will be equal to this one. This one. So it is mg by 15 pi RB square. So if you compare these two terms, then you can see that 64 by 81 is less than 1. Therefore, sigma A is less than sigma B. So B will break. This is correct one. And for third option, if we check RA is equal to, this is third, RA is equal to 3 RB. So sigma A will be equal to, I am putting the value of sigma RA in sigma A. So sigma A is this one. So RA is 3 RB. So this is 3 into 15, in fact 9 into 15. So this is 16 mg by 9 into 15 pi RB square. And if I compare sigma A with sigma B, you can see that 16 by 9 is greater, therefore sigma is greater than sigma B. Therefore option number A is correct because A will break. And if RA is equal to 5 RB, so if I substitute RA is equal to 5 RB in this term, sigma A here, so 16 by 25 will again be less than 1. Therefore sigma A will be less than sigma B. Therefore B will break, but in this option it is given that A will break. Therefore the correct options are only 1, 2 and 3. Now we move on the next question. In this question, you can see that there is a large rod whose length is equal to the radius of Earth, and hence it is hinged outside the Earth at somewhere in universe. It is hinged in such a way such that its lower end is touching the Earth's surface, and its density is rho, and its area of cross section is A, and Young's modulus is gamma. So we have to find out the extension in the rod due to the gravitational pull acting on the rod of Earth. And we have to imagine, we have to assume in fact that the only gravitational force acting on the rod is due to Earth. Now we can see that if you draw the diagram of the rod separately and let us find out the tension in the rod at some point on the rod at this point somewhere. So let us assume this distance is x and this is Earth. So from the center of Earth, this distance would be r plus x. So let us assume a small element of length dx here and its mass dm will be equal to dx into area into density rho. Okay, so the gravitational pull at this point will be equal to gm by r plus x whole square. Okay, so the force acting at this point will be I dm, and force will be equal to gm by r plus x whole square into dm, which is dx into a into rho. This is the force acting at this point. Now the tension at this point will be the total gravitational pulling force of this section. What I am trying to say that in the previous questions we have already done that tension at this point will be balancing mg of this section. So we have to find out the total gravitational pull of the lower end of the rod. So we have to integrate this force, and therefore the tension at this point x, which is at a distance of x, will be equal to integration of df. So T will be equal to integration of gma rho into dx by r plus x whole square, and limit of x would be from 0 to x. Therefore T will be equal to gma rho, and the integration of this term you can assume it as x, and integration of 1 upon x square is equal to minus 1 upon x. So you can write it down as minus 1 upon r plus x, and the limit will be from 0 to x. So T will be equal to gma rho into 1 upon r minus 1 upon r plus x. This is the tension at this point, which is at a distance of x from lower end. Now if we find out the stress, so stress at this point will be equal to tension per unit area, and tension is equal to gma rho, so a will be cancelled out, so it would be gm rho into 1 by r minus 1 by r plus x. And this stress will be equal to strain, which we have already used in many questions, that strain in this part will be dy by dx into gamma. So this dy will be equal to gm rho into 1 by r minus 1 by r plus x into dx divided by gamma, and integrating, the limit of dy will be from 0 to delta L and limit for x will be from 0 to r, where r is the total length of the rod. Okay, so this is delta L and it is gm rho by gamma. The integration of this term will be x upon r, and integration of this term will be minus ln r plus x, and limit will be from 0 to r. So delta L will be equal to gm rho by gamma. I am substituting r first of all here, so it would be 1 minus ln 2r you can see, and minus, then I am substituting 0, then it would be plus ln r. Now delta L will be equal to, I am substituting gm as gr square. We all know that gm is equal to gr square, and this g is acceleration due to gravity on the surface of earth. So this is rho and this is gamma and this is 1 minus ln2. You can see that because log a minus log b is log a upon b. So this is 1 minus ln2, and therefore if you compare it with this expression, this one, so p is 1 and q is 2. So p is 1 and q is 2. So p plus q will be equal to 3. So the correct answer for this is 3. Now we move on the next question. In this question, you can see that there are two plates. You can see the two plates. One plate is on the top and other is at the bottom. So there are two plates whose length is L and width is L by 2, but their thickness are different. The thickness of plate A is T naught, while the thickness of plate B is 3 T naught. So you can see that this thickness, this one, this is T naught and this is 3 T naught by 2. The Young's modulus of both of them are different. This is gamma naught and this is gamma naught by 2. And we have to find out the force constant of the composite slab. If we stretch this slab along the x-axis, then what would be the force constant K? So first of all, we know that if we use the spring analogy, then there are two springs. This is spring 1 and this is spring 2. They are connected in parallel and this is being pulled, this system is being pulled along x-axis. So in parallel combination, K equivalent is equal to K1 plus K2. Now K1 is gamma A by L and gamma for the plate A is gamma naught. Its area would be the area of cross section. Now you should imagine that plate A has a thickness of T naught and its length, cross sectional length is L by 2. So its area should be L naught, T naught into L by 2, and its length is L, this one. Okay, so K1 is equal to gamma naught T naught by 2, and K2 will be equal to gamma naught by 2 because its Young's modulus is gamma naught by 2 and its thickness is 3 T naught by 2. So it would be 3 T naught by 2 into the length is L by 2 and divided by the length, which is also L. So it is equal to 3 by 8 gamma naught T naught. So the equivalent K will be equal to gamma naught T naught 1 plus, in fact, 1 by 2 plus 3 by 8. So it would be equal to 7 by 8 gamma naught T naught. So P is equal to 7 and Q is equal to 8. So Q minus P will be equal to 1. So the correct answer of this question is 1. Now we move on the next question. In this question, you can see that there are two rods P and Q which are welded together and P is fixed on the wall. A force F is applied on this rod and the values of Young's modulus, area of cross section and length are given. So we have to find out the elongations and energy stored in the two wires. So let us use the spring analogy and let us assume that this is spring P and this is spring Q. So this is P and Q. So we know that in series combination, this is series combination, F remains same. So force in both of them will same and therefore Kp into Xp will be equal to Kq into Xq. And we also know that the in series combination Xp plus Xq will be equal to total X. Okay, so first of all, let us find out the elongations. Now we know that the total K equivalent of series combination will be Kp into Kq upon Kp plus Kq. And therefore, we can write down the value of K equivalent as equal to Kp is equal to gamma into 2a by 2l, and this is gamma a by l, and therefore Kq is equal to 2 gamma into a by l. So if this is equal to K, so this is equal to 2K. So K equivalent will be equal to, this is 2 by 3K by substituting these values in this one. So you can see that this is the K equivalent and the total extension will be X will be equal to F upon K equivalent total extension. So it would be F upon 2K by 3. And if we divide XP and XQ in this ratio such that XP by XQ is equal to KQ by KP, so we can write down that XP will be equal to KQ into X upon this total KP plus KQ, and XQ will be equal to Kp into X upon Kp plus Kq. So we can use these values and we can write down the value of Xp as Xp will be equal to Kq. Now Kq is equal to 2K and X is equal to 3F by 2K. So this is 3F by 2K divided by 2K plus K. So you can see that it is equal to F by K. Now XQ is equal to KPX. Now Kp is equal to K, so it is K into X, where X is 3F by 2K divided by this is 3K. So cancelling this 3 with 3 and K with K, so this is F by 2K. And we know that K was equal to gamma A by L. So we can say that XP is equal to F upon gamma A by L and XQ is equal to F upon 2 gamma A by L, where XP and XQ are the extensions in the two springs. So XP will be equal to gamma A by L. In fact, this is FL by gamma A. So it is FL by gamma A and xq is FL by 2 gamma A. Okay, so the correct answers are option number 2 and 3. Now if we find out the energy, so we know that energy in P will be half F square by Kp, and energy in Q will be half F square by Kq. Now Kp is equal to K and Kq 2K. So this is F square by 2K and this is F square by 4K. Okay, so we can say that the value of UP will be F square by 2 gamma A by L. So UP will be F square by 2 gamma A by L, which is option number 2. So this, and we also know that UP is equal to 2UQ. UP is equal to twice of UQ. So the correct answer will be option number 3 also. Okay, now we move on the next question.